Hello students, I welcome you all in this session of quick solution for All India AIATS test series for JEE Advanced 2020, test 4A, paper 1, code A and B, subject physics, test dated on 24th of November 2019. Let's start with question number 1. Here in question number 1, a photoelectric plate is initially exposed to radiation coming from a sample of hydrogen gas being excited electronically to second energy level. Later, when the same photoelectric plate is exposed to a spectrum of some unknown hydrogen-like gas excited to second energy level, it is found that ratio of minimum de Broglie wavelength of photoelectrons ejected due to hydrogen gas and unknown gas is square root of 6.1. For this new gas, difference of energies of first Lemon series and Balmer series limit is found to be 2 times the ionization potential energy of hydrogen atom. Work function of photoelectric plate is nearly K into 21 into 10 to the power minus 1 electron volt. Find the value of K. Well, we shall proceed with the calculation of the value of minimum de Broglie wavelength for the gaseous system. I would say it is definitely 1 by 2 mv square would be taken as delta E naught Z square for atomic number to be Z into 3 by 4 minus 5. From here I'll be getting this answer lambda to be equal to how much? H by P, or lambda would be written down as H divided by square root of 2m into delta E naught Z square into 3 by 4 minus 5. It's been given that the ratio of the de Broglie wavelength of the electron ejected due to hydrogen gas and unknown gas. So I'll just be writing down lambda of hydrogen gas and lambda of unknown gas. It is to be equal to square root of 6.1, and from here I'll be writing as for hydrogen gas Z to be equal to how much? 1, and for unknown gas it is to be Z. It is simply 2m delta E naught Z square into 3 by 4 minus 5 divided by 2m into delta E naught, and this value Z to be 1, 3 by 4 minus 5. Let it be this equation for the time being. Another statement is, for this new gas, difference of energies of first Lemon series and Balmer series limit is found to be 2 times the ionization potential energy of the hydrogen atom. From this statement, difference of energy of first Lemon series, it will be delta E naught into Z square into 3 by 4 minus series limit of Balmer series, it will be delta E naught Z square divided by 4. It is 2 times the ionization potential energy of hydrogen atom. It is 2 times ionization potential energy of hydrogen atom is how much? It would be delta E naught itself. So just calculating this part, we are getting the Z equal to how much? It is the value of 2. Once we'll put this value of Z is equal to 2 in this equation, there we'll be getting the value of phi to be equal to 2 into 21 into 10 to the power minus 1 electron volt. So from here we will be getting the value of K, that is to be how much? It is coming out to be 2. That is our answer for question number 1. Now we shall proceed to the next question, that is question number 2. Here in question number 2, P1 and P2 are 2 transparent plates having equal thickness T is equal to 40 micrometer each and refractive indexes of mu1 is equal to 2.0 and mu2 is equal to 1.5 respectively. S1, S2 are identical slits. The plate P1 transmits 100% whereas the P2 transmits 25% of incident energy. Without P1 and P2, the intensity at O is I. The intensity at O after placing P1 and P2 is x divided by yi. Then find the value of y minus x given x and y are co-prime. The wavelength of the incident light being lambda is equal to 4000 angstrom. If I assume the initial individual intensities at these 2 points being I naught, then here I shall have the maximum intensities of 4 I naught, and that actually being given as I. So if somewhere I need the value of I naught, it must be replaced at I by 4. Fine. This is the intensity at the central point initially. Now it transmits 100% of the energy and it transmits only 25% of the energy at this point. So looking into the part now, I need to find out what is the actual path difference of the interfering wave at point O. So I would simply say the path difference being here T is how much? 40 micrometer, refractive index is 2.0 and it is 1.5. So I would say it is 1 by 2 into 40 micrometer, or actually it is 20 micrometer. This is the path difference of the interfering wave. So further here I'll be calculating that how much this path difference is the multiple of the wavelength. So it is 20 divided by 4000 angstrom, that means 10 to the power minus 10. This one is 10 to the power minus 6. So here I'm getting this value to be how much? It is coming out to be 50. So the path difference is actually 50 into wavelength. That means definitely the wave interfering here, they will be interfering in a constructive manner. So the resulting intensity will be I resulting will be I naught plus I naught by 4 plus 2 into root I naught into root I naught by 2. That will be I naught by 2, or effectively it is 2 I naught plus I naught by 4, and it is 9 I naught by 4. We have just said that once I naught will be taken as I by 4, I will have resulting intensity to be, it is 9I divided by 16. So looking onto the option here, it is given in terms of x by yi. So x is 9 and y is 16. So now the value of y minus x will be 16 minus 9, that is coming out to be 7. So this is the answer for question number 2. We got the answer as 7. Now let's proceed to the next question, that is question number 3. Here in question number 3, a neutron strikes a hydrogen atom which is initially at rest and free to move. The initial speed of neutron is v0. After the collision, both neutron and hydrogen atom moves, making an angle of 30 degrees with initial velocity of neutron. Also, H atom is found to get excited to first excited state. If initial kinetic energy of neutron is x times the first excitation energy of hydrogen atom, then find the value of x. We are having a situation here where one neutron is making a collision with hydrogen atom and they are finally having the velocity v, initial velocity being v0, and this angle is how much? 30 degrees. So by principle of conservation of linear momentum, I would say mv0 is equal to mv root 3 by 2 into 2, or I'm getting this final velocity of this neutron and hydrogen atom, that is to be how much? It is v0 divided by root 3. Now looking into the energy equation, initial energy was 1 by 2 mv0 square. Finally it is 1 by 2 mv square to be taken as v0 square divided by 3 and 2 here. And another information is hydrogen atom is found to be excited to the first excited state. That means it will be delta E0 into 3 by 4. Now 1 by 2 mv0 square, this part is 1, and here it is 2 by 3 is equal to 3 by 4 delta E0. Also, the initial kinetic energy of neutron is x times the first excitation energy. That means it is, this one is x times into 3 by 4 delta E0. This portion, it is 1 by 3 is equal to 3 by 4 delta E0. Now this portion will cancel out. We are getting x to be equal to 3. So for question number 3, our answer is 3. Now we shall proceed to next question, that is question number 4. In question number 4, in the YDSC shown below, two slits are covered with thin sheets having thickness T and 2T and refractive indexes being 2 mu and mu respectively. The position of central maxima is shifted by a distance of n centimeter from central position of the screen. Find the value of n. Given value of small d to be 1 mm, capital D to be 1 meter, and T is equal to 2 into 10 to the minus 2 mm. Mu is equal to 3 by 2. Well, I'll just calculate the path difference of the ray coming from S1 and S2. For S1, it is, let's say, x. It would be how much? this distance is 2t, so I would be saying is 2 mu t plus t, and the path from here it is x2 is equal to 2 mu t. So it is very clear that the actual path difference of the wave coming at this point is how much? It is actually t itself. So to counterbalance that path, the central maxima would be shifting in upward direction, and we shall have somewhere here as the central maxima. I would simply say let this angle being how much? Theta. So it is d sine theta must be equal to t, or now we shall proceed to next question, that is question number 5. In question number 5, electrons having kinetic energy 30 electron volt is made to collide with atomic hydrogen gas in ground state, and 42.5% of electrons energy is used to excite the hydrogen atom. Maximum possible number of wavelengths y by capital D would be t. From here, first calculate the value of y as it is getting excited to nth energy state. So I would simply this answer to be equal to how much? E naught is coming out to be 13.6 electron volt centimeter. 1 minus 1 by n square must be equal to how much? 30 electron volt into 42.5%. 42.5%, that means divide by 100. Or 1 minus 1 by n square would be equal to 30 into 42.5 divided by 100 into 13.6. If we make a calculation, we'll be getting the value of n is equal to 4. It means the hydrogen gas would now be excited to 4th energy state. That means in emission spectra, there will be 6 different wavelengths. So question number 5, we are having the answer as 6. Now we shall proceed to the next question, that is question number 6. In question number 6, light of wavelength 520 nanometer passing through double slit of YDSC produces interference pattern whose variation of relative intensity versus deflection angle theta is shown in figure. The separation d between the slit is, that's been written down as k into 10 to the power minus 2 mm. We need to find the approximate value of k. I would say this is the distance or the angular position at which the first minima occurs. Should I write it down as d sine theta is equal to, for first minima it is how much? Lambda by 2, or d would be lambda divided by 2 sine of 0.75. On calculation, we'll be getting this answer almost very close to 2 into 10 to the power minus 2 mm. Just place the value of sine 0.75 here. Well, so for question number 6, we are having 2 as the answer. Now we shall proceed to the next question. In question number 7, nuclei of deuterium, that is D is equal to 1H2, and tritium, that is T is equal to 1H3, can fuse according to the following reaction to produce a neutron and an alpha particle. D plus T, that is producing one alpha particle and one neutron. Assuming binding energies per nucleon of deuterium, tritium and helium to be equal to 1.00 mega electron volt, 2.40 mega electron volt and 7.30 mega electron volt respectively, and neglect the kinetic energies of the nuclei before the collision. Find the kinetic energy in mega electron volt carried away by the helium nuclei approximately, or alpha particle I would say. First we need to calculate the Q value for this reaction. That would be binding energy of this term minus the binding energies of this term. It is 7.30 into 4 minus, for the tritium it is 2.40 into 3 minus 1.00 into 2. So how much this calculation is? That is the value for the Q. It is coming out to be 20 mega electron volt. Fine. Now let's think of the way the momentum will be shared. Let this being the helium nuclei or alpha particle and this being the neutron. If it is having the velocity v along this direction and this one is having the velocity v dash, I would say 4 mv dash must be equal to mv, or v would be equal to 4v dash. So the total energy that would be shared by this helium nuclei and the neutron, I would say it is 1 by 2, mass being 4m, and its velocity, I just said it to be v dash square, plus 1 by 2, its mass is m into v square, that must be equal to q value. So it is 1 by 2 into 4m v dash square, plus here v is equal to 4 v dash, it is 1 by 2m, it is how much? 16 v dash square. This is the energy. We need to find out the energy for the helium nuclei. It is 1 by 2 4m into v dash square, that is the energy. This is 1 plus here it is 4, it must be equal to q. So this is the energy carried away by the helium nuclei. It is coming out to be q is how much? 20, and this is 4 plus 1 5, so I would say 20 divided by 5, it is coming out to be 4 mega electron volt. That's the answer for question number 7. 4 is the answer. Now let's proceed to question number 8. Here in question number 8, two coherent monochromatic source A and B emit light of wavelength lambda. The distance between A and B is d is equal to 5 lambda here. If the detector is moved along the line BC perpendicular to AB and passing through B, this is the way the detector will be moved. Then number of minima observed is n. We need to find the value of n. This question is quite a simple one. I would say here the path difference being how much? 5 lambda. By the way, the detector will be moving from here and will be reaching to very large distance. The path difference will almost be reducing to 0. So in between, we shall have a path difference of 4 lambda, here 3 lambda, here 2 lambda, and somewhere around here lambda. So at these points, we shall have the maxima. And in between those of the path, we shall have a path difference of 4.5 lambda, 3.5 lambda, here 2.5 lambda, here 1.5 lambda, and here 0.5 lambda. So these points, this one, this one, this one, and this one. At these points, we shall have the corresponding minima. So how much it is? So 1, 2, 3, 4, 5. 5 different points will be there. So our answer for question number 8 is the value of n to be equal to how much? 5. Now let's proceed to next question, that is question number 9.